Good morning, everyone. I'm really pleased to invite you to the lesson Climate Change, what happens in the Arctic doesn't stay in the Arctic. The lesson will be conducted by Wielgopolan. She is our environmental specialist working in the Institute of Geophysics, Polish Academy of Sciences. And the lesson, in fact, was requested by teachers themselves. They wanted to have a lesson on climate change, and Ania agreed to do that. So I'm very happy for that. Okay, Ania, the floor is yours.
Thank you very much. My name is Ania. I work in the Institute of Geophysics, Polish Academy of Sciences. Today we'll talk about the Arctic from a little bit different perspective. I recognize many of you from previous lessons, but this lesson is going to be a little bit different, maybe less facts, but what I'd like to be the outcome of this lesson is a bit of consciousness, critical thinking out of the box. It will surely not exhaust the subject of climate change, its causes, consequences, and means of counteracting those changes. It will not even actually exhaust the subject of the impact of Arctic changes on the rest of the planet. First of all, because it's a very vast topic, but second of all, because we don't really know everything yet. There are constantly new studies, new models, new evidence. And this is more like an inspiration for future discussions, maybe in your classroom. I also would like to debunk some myths and show some phenomena that might not seem so obvious. But let's start with a short warm-up. How about your feelings about the Arctic? What are the words that come to your mind when you hear the Arctic? And you have 20 seconds to write something on chat. Anything that comes to your mind. Any description of the Arctic. What is Arctic like? I know you know quite a lot already because you had so many lessons on many topics related to Arctic. But what are your thoughts? Any thoughts? Okay, someone was following lessons, very good. Cold climate, tundra, auroras. Anything else? What is it like as a region? Okay, let's not make it too long. Because I did some research and asking myself before, and these are the answers that I received. It's cold, like you said, also monotonous, constant, distant, unfriendly, and uninhabited. These are the answers of persons who are not actually professionally connected to Arctic, and this is what came to their mind. And so let's start with cold. Let's start with cold. It usually is, but as you know, it's also rather relative, is it cold or not. By definition, from a meteorological point of view, the frontier of the Arctic is isotherm, and I hope everyone knows what isotherm is, plus 10 Celsius degrees in July. That means it's not warm in the summer. But lately, the average temperature in the Arctic is 7 degrees higher than the long-term average, and by long-term I mean 1979-2000. Actually, if you follow our Arctic monitoring system, which I encourage you to do, on a map you can see that in February on Svalbard it was much warmer than, for example, in Poland at the same hour, and it was a significant difference. What else? Unfriendly. It is relative as well, because it's all a matter of adaptation. It's a rather harsh environment, but there are animals and plants that managed to live there because they produced specific adaptations to the climate, to the environment. And if the climate becomes warmer, which we'd normally say more friendly from human point of view, those animals and plants are actually decreasing or being replaced by other species from the south in general. For example, Arctic fox that are replaced by more aggressive red fox from southern areas. As for distance, I can see we have schools from Poland, from Greece, from Romania. We also have schools from Italy on board. Yes, it's distance from this point of view, quite hard to reach. For example, to go to Polish Polar Station, Horsens, you need to first fly and then fly again and then go by ship. So it's quite far away. But we also have, in our project, we also have on board some schools from, for example, Faraway Islands on board. And this is literally an Arctic country. How about uniform? It definitely is not. There are parts constantly covered with ice, but also we have, like you already know, tundra or quite big cities. And it's not uninhabited. It's definitely not uninhabited because, first of all, indigenous people have inhabited the Arctic for thousands of years. There are over 40 different ethnic groups living in the Arctic now. I hope you will also have a lesson dedicated to them because it's a very, very interesting topic. But for now, there are 4 million people that inhabit Arctic. Most of them are not indigenous people, but it is a result of the migration from in 20th century. And the other myth that it's constant, immutable, monotonous, it is not. And this is what I'd like to talk about today. It is changing. And unfortunately, lately it's changing really, really fast, faster than it should. So it isn't exactly a constant, but rather a very variable region in many ways, and more of that later on. We're talking about the climate, so just a very short summary what climate is. Climate is basically the statistics of weather, which is a subject of research usually for over than 30 years, for a 30-year interval at least. It is measured by assessing patterns of variation of certain parameters like temperature, humidity, atmospheric pressure, wind, precipitation, and by precipitation we mean, for example, snow or rain. Atmospheric particle count, that is also important, and other variables over a long periods of time, like I said. This is how climate differs from weather, because in what weather only describes is a short-term condition. And as for global warming, you can see here on this image so-called climate zones. It's an image related to average temperature in certain areas. What global warming results in is redistributions of these areas. For example, only a 3 Celsius degree change in average mean annual temperature corresponds to a major shift in these areas because it changes isotherms, approximately 300 to 400 kilometers in latitude. What is the result? For example, species are expected to move either upwards in elevation to the mountains, we'd say, or towards the poles, that is, in latitudes, in response to those shifting climate zones. But how do we know all this? How do we measure things and compare those parameters in a long period of time? Here you can see that some facts, but only chosen facts and dates from the history of measurements. Of course, there are many, many more. Just to show you that people were interested in observations and classifications very, very early in history, even without very special equipment. You can see that 3,000 years before Christ, there were already discussions regarding clouds and ray formation. This gentleman here, this is Galileo, who is a very important figure for meteorology also, and who at the end of 16th century constructed a thermometer. Actually, you can see it on the image too, and it's an air thermometer, and now you can buy it as an accessory. This thing is actually a Galileo type thermometer. what else? What was very important date is, for example, when Celsius proposed one of the most common 100 degrees scale of temperature. But really, the modern meteorology, climatology, dates from 19th century, basically with electricity and telegraph that allowed us to send data and to give regular reference measurements. And this is when those reference measurements start. We call it the longest series of measurements. And then, of course, there are recent decades with the large increase of interest in climate change. Because we have now modern equipment and, most of all, satellite observations, which allow us to do a lot more on a lot bigger scale. Also, you can see here, what you can see here down in this slide are tree rings. Because there is also a branch of science called paleoclimatology, which allows us to compare data with from periods that happened many thousands of years ago, before humans even appeared. And this is thanks to sediments found in lake beds, tree rings like this one, and coral. So we have reference data, of course, not so detailed, from very long periods of time. Another questions, and I hope everyone can hear me and give me answers in 20 seconds. What do you think are the worst extremes recorded? And observe, that means only, not even in human history, but since the beginning of regular measurements. That is not such a long period of time. But what do you think was the highest temperature ever recorded, lowest temperature, heaviest hail? Hail, I think those who follow our monitoring system know what it is, but just to make sure, basically ice falling down from the sky. And what do you think was the highest precipitation in 1 minute? Just wild guess on chat, please. Plus 60, minus 70, okay. Anyone else? How about the heaviest hail ever recorded? And maybe where was that recorded? That is a tough one. And I think precipitation is the most difficult. So one more answer, please. Thank you, Thessaloniki, but let's make sure that everyone else is active too. Okay. Anyone else? So we have two different answers from Thessaloniki. Thank you. Let's find out. Actually, you were quite close, especially in the first set of answers. Highest temperature ever recorded, 56.7 Celsius degrees. That was USA in 1933. But the lowest temperature is 1983. That's not that long ago. And as you can see, it's almost minus 90 degrees Celsius degrees. That was in the Antarctic. It was recorded on Vostok Station. The heaviest hail, I think the image is not the one from Bangladesh, 1986, and I think the hail was even bigger. But you can see that it's like a giant ball of ice falling down from the sky, which can be actually really dangerous. That's why we call it an extreme weather event. And as for highest precipitation in 1 minute, that may not seem a lot, but you have to imagine more than 3 centimeters of layer of water everywhere, only after 1 minute of rain, that is Unionville 1956. Okay, we're talking about climate changing and how it influences, for example, distribution of climate zones and species, but is it really changing? I know you may have heard different theories in that it might not be that certain that the climate is really changing, or if humans really influence those changes. Well, I can tell you that from scientific point of view, there is no doubt, because there is evidence, and the causes of those changes are largely, I'm not saying that only, but largely anthropogenic. Where do we find this evidence? What you can see in this image on the left are ice cores. Ice cores from polar ice caps or polar glaciers. They're actually very, very long ice cores, can be several kilometers deep, and are made up of layers of ice that have built up over hundreds of thousands of years of snowfall. And when the snow fell, air became trapped within the snow and ultimately ended up as tiny bubbles and in the ice, like those shown in the photo on the right. And samples of the ice from different layers taken from those ice cores correspond to different times before the present and can be melted, so the trapped gases are released. And we can study what those gases contain. And what we know is that over the last 2 centuries, first of all, what we know is that the global mean temperature has increased by 0.6 Celsius degrees, and that this current trend goes beyond the natural variability. And we also know that link can be established between rising the level of atmospheric CO2, carbon dioxide levels, and global temperature. This warming of 0.6 can be attributed to human activities, industrial activities, which are very, very intensive in the last 2 centuries. Actually, the amount of carbon dioxide, CO2, in the atmosphere has increased by 35% since the beginning of so-called Industrial Revolution. So, since the beginning of very intensive burning of fossil fuels. Fossil fuels are coal or oil or gas. And also, human activity means clearing of land, deforestation, to create new space for industry and for new habitats for humans. Okay. So we have rising temperature and rising level of CO2. But has climate changed before? Because some say it is all a natural variation, the climate has already changed before, but that there are natural factors, variation in solar radiation, volcanic eruptions, etc. Yes, this is all true, this all influences climate as well, but there's evidence that factors that are linked to human activity influence the climate. Of course, even in human history before Industrial Revolution, changes also took place. You may have heard of so-called medieval warm period. Actually, I showed you the link to a very interesting video in your materials for enrolled classes. If you haven't had a chance to watch it yet, I encourage you to do so, because it gives a very critical thinking towards what happened then. But it's, for example, medieval warm period, or so-called Little Ice Age, when parts of Baltic Sea were completely frozen for a while. But let's take a look at scientific proof. Here you have 2 graphs. Have a look at the upper graph. The black line shows the variation in atomic composition of the polar ice cores. There are peaks in these lines, higher values, that are also highlighted by those gray bars. These temperature variations show that less carbon dioxide and less carbon methane correspond to ice ages, when the Earth was colder than it is now, and that more carbon dioxide and methane is present in warmer periods like now. This is consistent with what we know about the role of CO2 and methane in the atmosphere and in global warming, and so-called greenhouse effect. You can see, and I'll try to show you that. First, let's have a look at the second graph. You can see that the increase in carbon dioxide. Okay, let's try this. Increase in carbon dioxide begins here a little bit here. The blue line is the level of carbon dioxide. Here begin the early days of Industrial Revolution. This climbs very rapidly near the end of 20th century as we burn more and more fossil fuel. The final values are direct measurements, so this is what it is now. And the second interesting thing is that for 650,000 years, until the 20th century, the amount of carbon dioxide in the air was never ever higher than 300 ppm. That means parts per million. That is a certain value. So we were never higher than that, never more than 300. And now, by the beginning of the 21st century, about 116 ppm of new carbon dioxide has been added to the air during only previous 200 years, which is about equivalent to the weight of about 2.3 billion fully loaded Boeing 747 airliners. That is quite a lot. And this change is both far outside the range of natural variation, and this causes unprecedented changes of Earth climates in ways that are very, very different from the past. How about the Arctic climate? Arctic is very, very vulnerable as an ecosystem, as a region, because and now we observe that those changes that happen in our planet are much faster in the Arctic than in other regions. What you see here is a canary. It's an image of a canary, and why did I put that? A canary of Arctic climate is a sea ice extent. In older days, miners once had canaries to warn of rising concentration of noxious toxic gas. And for researchers working on climate change, sea ice extent is sort of a canary. It's like an early warning system showing that something is going wrong. Because for the Arctic, sea ice is one of the most important climatic variables. It's like a key indicator. It's because it's affecting lots of things like surface reflectivity, cloudiness, humidity, and so on. Okay, so what happens in the Arctic? Because of climate change, we have lower sea ice extent, thinner ice, acidification of oceans. The pH becomes lower. They're more acidic. Increase of temperature because there are melting glaciers, and thawing permafrost. That is also important. We'll come back to that. And when we have higher temperatures, we have more evaporation. When we have more evaporation, we have more precipitation. But, and this is very important and harmful to the balance of Arctic climate, it is rather rain than snow that is coming from the sky. As for acidification of oceans, so why is it so dangerous? You can see now on this image that oceanic organisms are not able to form, for example, their shells that are made of calcium carboxide. So they are dissolved by more acidic water. And due to increased carbon dioxide in the atmosphere, the world's oceans are about 30% more acidic now than before the Industrial Revolution. And again, Arctic is very, very vulnerable. Cold oceans, like those in the Arctic, are acidifying, are becoming more acidic, twice as fast as average. That influences shellfish, and problems with shellfish influence fisheries and the whole food web. And also it's dangerous to the plankton, which is used to a different environment. So what about temperatures? Some say that 2016 was the year of all-time records. As you see now, yes, this is annual mean temperature, and there's a clear trend that it's getting higher. And 2016, unfortunately we have a record. I was talking about ice, and sea ice extent is one thing, but also what is important, that the ice becomes thinner. And this image, I think, shows clearly that only in 30 years the ice became evidently thinner than it was before, and that also has negative consequences. So we're coming to the point why what happens in the Arctic doesn't stay just in the Arctic. We already know that Arctic changes are going, like I said, at least twice as fast as the rest of the world. But how does it happen? How does this 6% of Earth area affect the entire, maybe not the entire planet in the same way, but at least the entire northern hemisphere? There are several identified processes for now. And here are the most important. Albedo effect, release of organic carbon from glaciers and permafrost, changes in oceanic circulation patterns, and changes in global atmospheric circulation. Let's start with the albedo effect. The albedo is more or less how the Earth reflects sun radiation, or the energy that sun radiation brings. And satellite observations of Arctic sea ice cover over the last 30 years showed that the region has become visibly darker in color. With the loss of ice and less snow cover, it's clearly darker. And normally shiny ice snow reflects a very high proportion of the sun's energy back into the space. And as the Arctic loses snow and ice, there is only bare rock and water that absorb more and more of the sun's energy. Thawing permafrost. This is a very complex problem. Subarctic permafrost regions of permanently frozen land cover around 25% of the Earth. But this is not only the problem of buildings being destroyed because the permafrost is thawing, because it is a really big problem in subarctic areas. But there are also immense stores of trapped greenhouse gases in this permafrost, such as carbon dioxide and methane. And as the Arctic warms, these carbon reservoirs that are really hard to measure are expected to be released with hardly predictable consequences. And talking about permafrost, do you think that positive feedback loop is a good thing? It sounds positive, but is it really a good thing? Let's look at the example related to climate change. When the climate warms, the temperature in the summer is higher, so we use more air conditioning, even in the temperate zones when we did not used to use it. But to have air conditioning, to use more air conditioning, we need to buy and consume more energy. To consume more energy, we need to produce more energy, and mostly, for now, we produce it from fossil fuels. So if we produce more energy, there are more CO2, carbon dioxide, emissions. And those emissions cause climate to warm again. Then that is a positive feedback loop. It's not that positive. It's more an effect that is even causing the cause to become even more intensive. As for carbon system positive feedback loop, we see here that increased melting of polar sea ice influences reduced polar albedo and increased solar absorption. As a result, there is rising global temperatures and the increased melting of polar ice as a consequence. Another consequence of changes in the Arctic are threats to ocean currents. Ocean currents are a very, very vast topic. Those of you who participated in a lesson dedicated to northern fisheries know that it influences everything, fishing, for instance, but not only, but the whole climate, weather in whole Europe, especially so-called Gulf Stream. One of the consequences of the ice melt is the release of fresh water, which is not salty, into the ocean environment, making it less salty in certain areas. And it is changing local northern sea circulation and possibly impacting more broadly on oceanic circulation across the North Atlantic. And this is, like I said, this is a serious problem not only for fishing, but for agriculture, for extreme meteor events, because ocean currents shape weather for very, very large areas. As for fisheries, some Arctic fisheries will likely disappear if this process continues, not only impacting our food, but economies of Norway, Russia, which might not be able to supply us with our favorite salmon or trout. Okay, so maybe we can have a tiny break for a short video showing how the summarized ice cover changed over a long period of time since 1979. Hope you can all hear it well. Okay, this was an NASA animation. So, what happens in the Arctic doesn't stay in the Arctic. We know what's going on for now, but what is the evidence and what are the projections? For now, we know that we have more extreme temperature fluctuations in the northern hemisphere. We all observe very hot summers, cold, snowy winters, even in the southern Europe, and snowstorms. We see changing distribution of precipitation. We tend to observe wet summers, but on the other hand, very heavy drafts, which are very dangerous for agriculture. Also, we observe, and we're likely to observe more in the future, of the sea level rise and weather extremes. As for weather extreme events, the decade from 2000 to 2010 brought record-breaking extreme weather throughout Europe and throughout North America, Western Russia, Australia. And this extreme weather ranged from hottest summers, wettest autumns to the strongest cyclones ever experienced in these regions. And stronger northerly winds and weaker so-called westerly jet stream that blew cold polar air over North America is what caused, maybe you remember, those extremely catastrophic cold, snowy winter 2014-2015 in USA. As for sea level rise, you can see also it's a graphic projection of what we might expect. During the period from the beginning of 20th century till 2010, global mean sea level rose substantially. That is average 0.19 meters. It might not seem a lot, but trust me, from the scientific point of view, it's really a lot. It is projected that middle and low latitudes, where there are most human population centers, which is east coast of North America and Europe, will be very, very badly affected, more affected than other areas. And we have to remember that 13 out of 15 of the world's largest, most inhabited cities lie in coastal plains. And that is making them particularly vulnerable to rises in sea level. I'd like to show you another video, which is not presenting what is already happening, but actually what might happen. What if all the ice melted? Okay, that was a bit of dramatic vision. But I don't know if you noticed that if all the ice melts, it is estimated that the sea level would rise about 70 meters, and you saw all the large major cities all over the world that would be badly affected. It's not that it's going to happen in 2 weeks, but we have to make sure that it doesn't happen at all in a foreseeable future. So what can be done? I'd like to show you some maybe wild ideas that might seem wild for a moment. Let's start with the newest idea. One thing, this is so-called geoengineering, which is quite controversial because it is said that it affects natural processes which are very complicated. It affects them too much, and the consequences might be hardly predictable. But let's have a look at the ideas. The newest idea might seem rather crazy. A professor from Arizona thinks that 10 million wind-powered pumps should be placed over the sea cap. They would pump water to the surface of the ice. It would freeze then and thicken the cap, which would and this project would cost no less than $500 billion. But United Nations Convention of Biological Diversity ruled it out. It's such an open air and large scale and geoengineering, it's hardly likely to happen. And scientists around the world are developing or thinking of developing tools to try to stop the temperatures from rising. Another one is wrapping Greenland, like literally wrapping Greenland in a blanket, by covering the valleys that for darker areas we talked about earlier. Therefore, if they are dark, they are attracting the sun heat. This professor Jason Box from Ohio hopes to significantly slow the melting of the glacier by wrapping Greenland with a blanket. Hungry Ocean, another idea. Another professor from the Climate Foundation from Hawaii believes that ocean could absorb much more carbon dioxide from the atmosphere by creating plankton blooms. That means that by mixing the water, nutrient-rich water in the colder depths with warmer surface water, by placing again huge wave-powered pumps on the swells of North Pacific. Basically, he wants to mix the ocean up. Space sun shields, that is interesting. Professor Angel, who helped to create world's largest telescope, so he's a serious scientist, believes that the power of the sun, the amount of energy we're receiving, could be reduced by placing a giant sun shield in space. That would be a 100,000 square mile sunshade made of trillions of lenses that would reduce the sun's power, but only by 2%. Raining forests. Another scientist, a consultant environmental engineer, believes that extra forests could be generated by dropping from the sky tree bumps from the plane. There would be seedlings dropped in a wax canister full of fertilizer that would explode by hitting the ground, and that would grow into a tree. And actually, it was once used. The method was already used to regenerate so-called mangrove forest in Louisiana after Hurricane Katrina, when everything was destroyed. Another idea is pretty similar to previous ones. A brighter world, it's called. An engineer from Edinburgh believes that clouds can be created to protect the world from extra power of the sun. And he proposes forming clouds above the ocean by sending salt into the atmosphere. Let's have a look at the last one, maybe fixing carbon. A Canadian scientist believes that he can create a machine that sucks in ambient air and sprays it with sodium hydroxide. and then expels it as clean air. And then carbon from the air would be captured and stored underground. But just to finish our today's lesson, why don't we go simple? How to limit our individual carbon footprint. Here's what you could check. Here's a so-called carbon footprint calculator created by WWF organization. You just fill in a simple short quiz divided into areas of activity: food, travel, home, and buying, using stuff. And this is and what you receive as an outcome is how badly you and I, because everyone affects the environment, everyone is causing CO2 emissions. What are we producing, and therefore what should we do to limit this? So what I'd like you to do is think yourself what you can do personally. Here are some only basic ideas what could be done to limit human impact on climate change. As you remember, it is all about fossil fuels, almost all about fossil fuels, all about energy consuming. So counteracting those changes should be basically all about energy saving. Here are some more or less obvious ideas, like I'm sure you know that it is better to travel by bus than by car every time, or it is best to travel to use bike, for example, to go to school, but it is not also always possible. And I don't know if you are aware that you can also help environment by changing your diet a little bit. I'm not saying that everyone should go vegan, but limiting meat consumption can help the environment significantly by limiting CO2 emissions. So this is a small voluntary homework for you to find 5 easy things you can do to limit energy use, and by doing small things to counteract the global climate change that is influenced in a very large part by processes going on in the Arctic. This is it from me. Thank you very much. If you have any questions, I can see that I exceeded the time I promised to use a little bit. I'm sorry for that. But if you have any questions, go ahead and ask them. And if you maybe have any questions later, you can write me via email. Here's my email, and I always try to answer. Thank you very much. I think we'll wait for a couple of for a couple of, I don't know, 1 minute or two for your questions if you have any, and if not, or if you have to leave now for other classes, thank you for participating. Thank you.